Hello everybody, let's get started with neural networks. Initially, we'll try to understand some basic fundamental concepts of neural network. Then we'll do our hands dirty with some raw level TensorFlow coding for neural networks. This is the reference web page typically followed in Stanford as well. Okay, you may have a note on this, wholehouse.org. Thanks to the people who created this. We'll be using this as a base reference for all the notes and mathematical understanding. Let's proceed. So first, let's understand why do we need neural networks. Okay, and let's try to connect with machine learning. This is a pretty interesting understanding that we're gonna have now. Okay. Now, in machine learning, we invested a lot of time and a lot of work were done to do featureization, finding which are the important features, finding what are the important derived features. Derived features means you have, say, you have 5 columns. Like you can say one example of derived features as taking product of 2 values in 2 different columns, and that will be derived feature out of this, or square of a particular column, right? These are derived features. So over last a decade, a lot of people were trying to do a lot of featureization stuff. That means how to find important features or derived features from the data. Now, okay, this was fine and this was doing great with small amount of features. Okay, but with unstructured data like images, videos, audios, all this in coming into the picture, things just got a little more complicated. Okay, let's take an example of an image of say 100 cross 100 pixel image. Okay, so number of features in this case is 10 raised to the power 4, and number of derived features can go way beyond computation can allow. Okay, because we can have one column from here and the column from here, or a square of it, cube of it, all the possibilities of it can really explode. So it is really difficult to find what are the important features. Now that is where neural network kicks in. It really converges really well when the number of features explodes. It actually does featureization for you. Okay, to put it in simple line, neural networks helps you find important features. You don't have to do all the featureization by yourself. It will find how important features for you and do the prediction or classification using that. Let's proceed. As let me build on top it. Say for example, we have n is equal to 100, where n is the number of columns. So just with taking cube, that means the possibility of derived feature is just cube here, you get around 170,000 features, which is way beyond, and you can imagine how things go beyond that. And if it is an image, okay, computer vision would not be possible without neural network kicking in. Okay, if it is an image, see this example of car, you have 50 cross 50 pixel, so in all there is 2500 pixels. So if you try to find derived features out of this 2500 pixels, okay, or this 2500 features, okay, it would be this 50 and followed by 6 zeros. Way too much for a computation to handle. Okay, now without putting in a lot of historical perspective, which we can of course go deeper later on. Okay, the thing is, a lot of research has happened over the last 3 decades in this landscape. A lot of people had to be really given credit for doing extensive research in this area, even though it was not fruitful because of lack of computation power. And how important computation power was for the the recent development or the research that happened in neural networks is we can see by the number of research papers that came out in last 5 to 7 years. Okay, so now that computation power is cheap and really available for researchers, we can see explosion in this area, at least in research area. Okay, so people wanted to mimic how our brain worked, and that is what typical neural network is. They wanted to find out how our brain, can solve such complex problems, right? They wanted to mimic it, and that is typically what it is. And we'll try to understand the correlation between brain and artificial neural network. Let's see. You can see that this diagram here. So what we have is this is a typical brain cell, or you can neuron, the real neuron. Okay, so what you can see is dendrites over here. Okay, this tentacle sort of structure, this is dendrites over here. Okay, you can see these dendrites are the thing which will get data from different places. It can get data from another neuron itself. It can get data from other sensors like your brain, like your eyes, like your ears, and other things. Okay, so it can get information for you, in short. This is the nucleus part of it. On getting the information, the nucleus part will do the processing. Okay, it is nucleus part will do the processing. Okay, on doing the processing, it generates some output. Okay, so the output is coming out of this axon. Okay, so you have dendrite, which is receptors, which is the data receptors, the nucleus, which is the processing unit, and the axon, which is typically the output channels. It can of course output to another neuron. You can have this multiple layers of neurons connected to solve complex situations. Okay, so let's understand it this way. You have one layer getting some information, doing some processing for it. The output of this layer goes to another layer. The output of this layer goes to another layer. So in brain, you have most of the processing is finished in 7 to 12 layers. Okay, so this entire experiment was done on a cat. Okay, I'll cover these details in a different video. So I believe we now understand how how a typical neuron looks like. Okay, so let's now try to understand how an artificial neuron looks like. Okay, then we'll try to make multiple layers using this artificial neuron. Okay, similar to our actual biological neuron, we have input channels, as you can see here. Okay, and this is how artificial neuron, these are different features. Okay, so if you have three features, so this is one feature, this is another feature, this is the other one. Okay, these are three features. These three features comes to this processing unit. This is similar to your nucleus, the processing unit of neuron. Okay, this gives some output which is coming to axon. Okay, so this is how your basic artificial neuron is. Okay, you can call this as perceptron as well. Okay, this is the basic unit. So you have these features coming in from here. This is the processing unit. This is the axon, the output of it. Okay, this is the processing unit. Let's now try to understand how is it represented mathematically. This is the vector for features, as you can see here. X0, which is not shown in this figure, is typically your bias. This is that value which is independent of feature information, okay, but impacts the output. Okay, so bias is that information which impacts the output without being dependent on the feature. X0, this is one input. X1, X2, X3, these are different feature values, as you can see here. And you can see this theta 0, theta 1, theta 2, theta 3. These are your weights which will be associated with these feature values. Doesn't it look very similar to linear regression, logistic regression, where you have feature values and the corresponding weight to that feature? Okay, so if a feature is important, the weight will be higher. Just a similarity that we can understand over here. So we can see that a logistic regression or a linear regression can be very easily implemented with single layer of perceptron. Okay, or artificial neuron, as we can see here. Okay, so how to implement this? We can see x0 into theta 0 plus x1 into theta 1 plus x2 into theta 2 plus x3 into theta 3, and the resultant will be the output, and that will be coming out of the axon comparing to the biological neuron. If you want to see multiple layer of it coming into picture, okay, so this will act as input layer. These are the three features coming in. This is the middle layer. This is the output layer. So you can say this is the hidden layer, this is the output layer, and this is the input layer. Okay. So the middle layer, as in the previous diagram, was consisting of only one neuron. You can see three neurons here. So there are three possibilities of computation that is kicking in over here. Okay. We'll try to understand this. Okay, so let's now try to understand few jargons around neural networks. Okay, one thing we have already discussed is bias. Remember, it is that value which impacts the result without being dependent on the features. That is why it does not have any feature information associated with a constant number in this case. Okay, weights are the values that get associated with features. So in this case, so we can have say x1 is coming to A3, x1 is coming to A2, x1 is coming to A1, right? So the value x1 is getting as an input through 3 different nucleus or similar to nucleus. These are activation units. We'll discuss these later. These are activation units. So this is one value, okay, x1, which is going to all of them. But remember, what is the difference? Difference is the weightage to which it is going to all of them. So you can see here, this is one weightage, this is another weightage, this is another weightage. So to understand it, what is happening, each nodes or units, that's a technical term that people people try to use to understand this. These are known as units. These are known as layers, layer 1, layer 2, layer 3. This is units. So each unit of the previous layer is getting connected to each unit of the following layer. Like in this case, x1 is getting connected to this node is connected to all of this. So all of this is connected to each other. That is why it is known as fully connected neural network or deep neural network. Okay, we'll see a lot of variations as we proceed further. In the beginning, we'll try to understand how this fully connected neural network works. Okay, so one thing we understand from here, each of these nodes is connected to all of this, and each of these nodes will have different weights when it is connecting a different way. So how many weights are there? To put it simply, how many weights are there between layer 1 and layer 2? Okay, it is 3 cross 4. Okay, the maths is this next layer has 3 units, so 3, and number of units in the previous layer plus 1. Okay, so 3 units, so it's 3 cross 4 is the total number of coefficients or weights. Okay, this layer is 1 cross 4. I believe now we understand how to calculate number of coefficients between each layer. So total coefficients will be this plus this. We'll proceed further to understand these things. Okay, so as you saw here, these are known as activation. So this Aij, right? Let's see this. Aij is there. This Aij, where I is unit. So in this case, you can see unit 1, unit 2, unit 3, and layer is j. Okay, this is the layer, the second layer. So you can see this, the value that is on top of it, 2, 2, 2. This is the layer number. This is the unit number, right? So these are known as activation units. Okay, and if you want to understand the maths that is happening over here, let's see this. So as we discussed, what is the matrix size over here? Is 3 cross 4. So you can see this is 1. This is theta is the weights between this layer and this layer. So theta 1, 0. Let me draw it. Okay, so this is, I'm talking about between layer 1 and 2. This is layer 1. This is layer 2. Okay, this is, okay, so as we discussed earlier, this is 3 cross 4. Okay, so 3 rows, 1, 2, 3, and 4 columns will be there. 1, 2, 3, 4 columns. Okay, now this value gets multiplied with this weight. So we have, what we want to do, we want to find this value, the value at this point. Okay, so it is theta 1, 0. Okay, this is theta 1, 0. This is theta 1, 1. This is theta 1, 2. This is theta 1, 3. Okay, so this guy, okay, we can see this x0 coming in picture. X0 is not visible here. This is the bias value. We'll just mention it so that we don't complicate things. X0. Okay, so x0 into theta 1, 0. Right, x1 into theta 1, 1. x2 into theta 1, 2, x3 into theta 1, 3, right? So this, using the weights and the feature values, it computes the output value, and you can see this g over here. This g is known as activation function. Okay, this g is known as activation function. This g, we'll discuss a lot about activation functions. There are things like, sigmoid, ReLU, tanh, and many more. We'll discuss that. But this is some function which will be applied over this value that is coming out of it, and the output is the final value of A12, and this is how all these values are calculated. And eventually after this layer, okay, you get the values of A1, A12, A22, A32, right? And you use the coefficients and in this layer and compute this value. Okay, and this is the eventual value. So if it is a regression, linear regression, this value will be continuous in nature. If it is logistic regression, it will be some discrete value. I mean, based on the activation, based on this G value, we will be classifying which class is getting classified into. I believe it was clear till now. We'll continue this topic in the next video. Thank you.